Okay, welcome to this question about esters. Figure 4 shows an incomplete mechanism for the reaction of an ester with aqueous sodium hydroxide. Here we've got figure 4, and we have step 1, step 2, and step 3. You can see it shows arrows here, transfer of electrons shown through curly arrows. And if we look at the first question, it's 7.1. It says add 3 curly arrows to complete the mechanism in figure 4. So looking at this first diagram, we can see carbon is supposed to only have 4 bonds around it. Well, a maximum of 4 bonds. And if this was to actually form bonds here, we'd end up with 5 bonds. So if this OH group is going to donate an electron pair to the carbon, it means that carbonyl double bond is going to have to break to allow there to be only 4 bonds. Of course, that then donates some electrons to the oxygen. And that gets you your first mark for that curly arrow. Now, the second curly arrow, we've got this step here. You can see this intermediate. Again, 4 bonds. 1, 2, 3, 4. So what's going to happen? Well, the oxygen with the lone pair is redonating its electrons to form the carbonyl bond again. That would be 5 bonds again. We need to snap a bond off. But which bond do we snap off? That's the big question. Which of these bonds should go? It's actually this bond here. Now, how do we know it's this bond that's going to break off? Well, if we look here circled in blue, we can see what the result of the breaking of the bond is. So it has to be that bond there that's breaking. And of course, it gains a lone pair of electrons, that oxygen. So it would match perfectly with what I've circled in pink here. Now we need to show another bond, another curly arrow, and another movement of electrons. We can see here that the hydrogen is forming a bond with that oxygen. The lone pair is going from the oxygen with the negative sign to the hydrogen. Now hydrogen can only have one bond, so it can't continue to be bonded to the O, the oxygen, and form a new bond with the oxygen with the lone pair. So what does it do? It separates and breaks itself away from the oxygen here, and we can draw a curly arrow to show that. It's going to donate its electrons back there, and that makes sense because when we look at the step down below, we can see that the oxygen atom attached to the carbon with the carbonyl group has a negative sign over here circled in pink. So we can see that these two match up perfectly. So that's where the bond and that's where the pair of electrons end up. Okay, that's your 3 marks for the 3 curly arrows. Now name the type of reaction shown. Well, this reaction is base hydrolysis, or hydrolysis, however you like to say it. Why is it hydrolysis? Well, look, I've got one product. I'm going to circle it in blue here. One reactant, sorry. I've got one reactant and 2 products. So there's been splitting, and lysis means to break. Now, why is it base hydrolysis? Look here what I've circled in blue. That gained a hydrogen, and when you gain a proton, you are acting as a base. So that's why we call it base hydrolysis. Now 7.3, deduce the role of the CH3O minus ion in step 3, shown in figure 4. So let's go back up there and have a little look. If I circle it there, the CH3O minus ion, what is its role? We just discussed this. What atom is it gaining? Well, look what it's sending its lone pair on the O minus 2. It's sending it to the hydrogen. So it's gaining an H plus ion because technically that's going to snap off and become an H plus ion before it joins to that lone pair. So when you gain a hydrogen ion, what are you? You're a base. So it's accepting a hydrogen, therefore it is acting as a base. Brilliant. When you're a base, you're a proton acceptor. Let's look a little bit closer before we do the final question, which is a 1 marker. Let's look a little bit closer at this base hydrolysis. So this is an ester that I'm drawing here, and this is a nice simple ester. It's methyl and propanoate. So it's come from methanol and propanoic acid formed in a condensation reaction. Methyl propanoate. It's an ester. Ester link there in the middle. Now we can hydrolyze this ester link. We can break this ester linkage, and with a hydrolysis reaction with water under acidic conditions, and we're going to form methanol and propanoic acid. So methyl propanoate is broken into methanol and propanoic acid, and I've drawn in blue where the hydrogen, the oxygen have ended up. Now let's look at base hydrolysis, which is slightly different. So we're going to look at base hydrolysis now. So what I'm doing now is I'm going to draw another ester. This ester is a very large ester, a triester. Okay, involves three separate esters all bonded together, and it's an ester like we find in vegetable oil. Now this has got CH2 16 times, so a really long side chain coming off the carboxylic acid part of the ester. And if we use sodium hydroxide, which is a base, we're going to need three of them because it's a triester, so we need to break three ester links. And this is called base hydrolysis. And essentially, we're going to split this into an alcohol. Now, this alcohol is going to be glycerol, otherwise known as propan 1,2,3 triol. But instead of getting a carboxylic acid like we make with the acid hydrolysis, we're going to get a carboxylate ion, sodium carboxylate. And the difference is that the hydrogen atom on the carboxylic acid on the left is replaced with a sodium ion, an Na plus ion. So this hydrogen I've circled in yellow is going to be replaced with an Na plus. Okay, so you still get an alcohol, although it's a triol, but this time you get a sodium carboxylate instead of a carboxylic acid. And there it is. And this sodium carboxylate is actually a salt, which is soap. So for the final question, a triester in vegetable oil reacts with sodium hydroxide in a similar way. We've just looked at that reaction. Give a use of the product. Well, it's the sodium carboxylate and it's used as soap. There we go. Let's get to the marks.
You're still here? It's over.